Assalamualaikum and a very good day to our lecturers. We are from Group 29. We want to present briefly about mechanical design and analysis of post-mounting bracket, a project for subject Computer-Aided Engineering. Before we start, let me introduce our members. I am RABI'ATUL with number metric 2014027005. My fellow group mates are Wan Nur Hidayah and also Ifa Amira. Aim of this project is to design and develop an optimized bracket that exhibits the lowest possible mass while maintaining the highest factor of safety and minimal deflection. The background of the problem in developing an optimized bracket with the lowest mass, highest factor of safety, and minimal deflection involves several considerations which are weight reduction, strength to weight ratio, structural integrity, and factor of safety, deflection, and stiffness. Titanium is a lightweight metal that offers high strength relative to its low density. It is about half as dense as steel but still maintains good strength. Titanium is known for its excellent corrosion resistance and is extensively used in the aerospace industry as well as in automotive, marine, sports equipment, and medical devices. It provides weight reduction without compromising strength and durability. Although titanium can be more expensive and challenging to work with, its desirable properties make it a preferred choice when high strength and lightness are essential. Titanium is commonly used in mounting brackets due to its unique properties that make it well suited for such applications. These are the example uses in mounting brackets. Titanium is significantly lighter than many other metals, including steel. This makes it ideal for mounting brackets as it helps reduce the overall weight of the structure of system where the brackets are used. Despite its low density, titanium has excellent strength properties. It offers comparable or even superior strength to some steels, ensuring that titanium brackets can withstand the expected loads and forces without deformation or failure. Titanium exhibits exceptional corrosion resistance, making it highly suitable for mounting brackets in various environments. The combination of titanium's lightweight nature, high strength, and corrosion resistance results in durable and reliable mounting brackets. Titanium mounting brackets find applications in various industries, including aerospace, automotive, marine, and sports equipment. In summary, titanium is favored for mounting brackets due to its lightweight construction, high strength corrosion resistance, durability, and reliability. These properties make it an excellent choice for specialized applications that require dependable and lightweight mounting solutions. So this is a several method to create a 3D model construction. As shown in figure here, it is a basic shape that has met the dimensional requirement outlines. Once the initial design was established, further modifications and optimizations were made to improve the bracket's performance and match the project objectives. These modifications included adjusting the thickness, adding fillets and chamfers, optimizing the hole locations, and refining the overall shape for improved functionality and aesthetics. We create the model until it meets the specific requirements. The constructed 3D models were validated for accuracy and consistency with the provided outline and project objectives. So we have choose titanium as our mounting bracket material. Next, in Katia, we check the properties of mass. The mass for the bracket is 0.631 kilograms. The Young's modulus and Poisson ratio value are 1.14 times 10 exponent 11 meter per meter square and 0.34. By using advanced CAD software and employing a systematic approach to 3D model construction, the team was able to develop precise and comprehensive representations of the post-mounting bracket. These 3D models form the foundation for the project's subsequent analysis and optimization processes. Next, I will pass this presentation to Wan Nur Hidayah.
Here is the method we use in our project. The first step is to define the loading condition. This is include specifying the type of loading, the magnitude of the loading, and the location of the loading. The two faces at the hole are where the force will be applied. This face should be strong enough to withstand the force without breaking. The force will be transferred through the face to the rest of the structure. The negative direction, in this case, is downward, and 300 Newton is applied for the force. The next step is to define the boundary condition. This is include specifying the degree of freedom that are constrained and the value of the constraint. The two holes will be used to connect the structure to fit a support. Two holes have 8 faces. The 8 faces will be restrained from moving in any direction. The 8 faces should be strong enough to withstand the force that will be applied to them. The force will be transferred through the face to the fixed support. The analysis was performed for the thermal stress using the following parameter. Initial temperature at 35 degrees Celsius, final temperature at 115 degrees Celsius, and the thermal coefficient is 9.5 exponent 6 Kelvin. And then we define the free vibration analysis considering the mesh size, boundary condition, and material properties. And then perform a model analysis to calculate the natural frequency and mode shape of the structure. And lastly, we collect the result from graph and the result from tabular data. So method for mesh configuration. The mesh is created using a square mesh element. The mesh size is 3.0 mm, meaning each element is 3.0 mm long. The total number of nodes is 15,407, meaning the node is at each corner of each element. The total number of elements is 7,873, meaning the bracket is divided into 7,873 elements. This is a relative fine mesh, and the finite element analysis result will likely be accurate for this project analysis that our team will be used.
Hi and hello, my name is Ifa. So I'm going to continue to present about the result for this project. So result for linear static analysis achieved with the targeted value of the criteria, and then for equivalent von Mises stress, the maximum value is 296.9 megapascal, and for the maximum value of total deformation is 0.4013 millimeter. So the maximum value occurs at the bracket that have colored red. As for stress, it occurs at the two holes of profiles that have fixed point, and then another one for deformation is at the end of the bracket. Next, the result for thermal static analysis. The equivalent von Mises stress with thermal change, the maximum value is 3 to 6.21 megapascal, and without thermal change is 76.56 megapascal. For total deformation with thermal change is 0.7025 millimeter, and without thermal change is 0.6417 millimeter. The maximum value occurs at the bracket is colored red. Next is the result for free vibration analysis. For natural frequency result, so from number shape 1 until shape 5 with mode 2, mode 3, mode 4, mode 5 and mode 6 with their own frequency, and for the graph it's ascending order. So this is total deformation for the 5 mode, which is from shape 1, shape 2, shape 3, shape 4 and shape 5 with a different value maximum of total deformation. Discussion linear static analysis. This is the geometrical design that relate to structural analysis, load distribution and stiffness and deflection. The material is related to height, strength to weight, ratio, corrosion resistant, and also factor of safety. The importance of FOS in design is safety of structure, material selection, and reliability and durability. So the reason from the result obtained, when the force concentration, when the force applied, the constraint boundary condition result in higher stress level, and then when the force applied induces a bending moment, causing the end of the bracket to experience greater deflection, and then fixed support provide increased stiffness and resistance to deformation. Discussion for linear static analysis. The factor that contribute the different result is for the stress is thermal expansion, temperature changes, the material also will expand and contract, and it will change the structure dimension. And then for thermal gradient, it causes various locations to experience different thermal expansion and contraction, so which cause an uneven distribution of stress. For total deformation, have thermal extension, when material expand, the temperature rises, which leading to more overall deformation, and differential thermal expansion, the differential thermal expansion and subsequent changes in overall deformation. For the tendency bracket to failure is thermal stress, the material expand as the temperature rises, leading to more overall deformation. And for material behavior, it will change due to heat, which may impact how it fails. And then for fatigue, temperature variation can speed up the fatigue process and cause crack. And then also differential expansion can lead to localized deformation, stress concentration, and potential failure spots.
Conclusion for our project is the project aimed to design, analyze, and optimize a post-mortem bracket using CAD and CAE tools. The main objectives were to select appropriate material, ensure load-bearing capacity, and optimize the design. The bracket was analyzed using finite element method (FEM) approach, applying a linear static analysis, thermal stress analysis, and free vibration analysis, modal analysis. The result of the analysis show that the bracket design meet the specific criteria and demonstrate superior performance. The natural frequency result help eliminate resonance, evaluate structure integrity, and enhance performance, and also support failure analysis. Based on the result of the analysis, several suggestions or recommendations were made to improve the structural strength of the bracket, including using a more durable material like titanium alloy and redesign the mass reduction. And lastly, in conclusion, several factors can influence the result of computational analysis, including the accuracy of the input data, the quality of the mesh, the selection of the boundary condition, and the choice of analysis method. To improve the accuracy of the analysis result, it is important to ensure that the input data is accurate as possible and that the mesh is of a high quality and accurate size. The selection of boundary conditions should be based on the physical behavior of the system being analyzed, and the choice of analysis method should be accurate for the types of problem being solved. It is also important to validate the analysis result by comparing them with experimental data or analytical solution, and to perform sensitivity analysis to determine the effect of uncertainties in the input data.